Attends, je suis basse. Ah, mais ça veut dire qu'il faut que je reste là, en fait. Ah.
Hello, so thank you very much for coming. So I have the pleasure to introduce Chloé Michaut today, who's coming from Lyon. So Chloé is a professor at the INS in Lyon, and she's going to talk about Mars and the InSight mission in Mars. So Chloé did a PhD in Paris in geodynamics with Claude Jaupart, and then went for a postdoc to Yale, where she worked on the volcanology, and then was hired as a professor in Paris to work on the geodynamics, the evolution, the structure of planets. And now she's a professor in Lyon, and she's been involved in this Mars mission, and I guess this is what she's going to talk about today. So thank you, Chloé.
Hola, muchas gracias por venir aquí hoy. Lo siento, pero voy a hablar en inglés. So I had the chance to be part of this InSight mission. The InSight mission was a NASA mission that visited Mars for 4 Earth years, 2 Mars years, in between 2018 and 2022. And I will, yeah. Ah, esto. Sí, de acuerdo. Okay. So InSight visited Mars for 2 Mars years, 4 Earth years, in between 2018 and 2022, and I will tell you what we discover with this mission. So not all of this is the work of a team, and I was part of this team. My specialty is geodynamics and the evolution of the thermal evolution of a planet, and most of this work was in seismology. So Mars InSight is part of the spatial exploration of Mars, and spatial exploration of Mars has been ongoing for about 50 years. Mars InSight is the 9th successful landing on Mars. Since the landing of InSight in 2018 on Mars, there have been 2 other successful landings, and most of these landings were made by NASA, tens of them, and one was Chinese, the Tianwen mission in 2021. So most of these, as Mars is at a distance from the Sun that is compatible with liquid water, most of these missions were studying Mars with the aim of discovering traces of ancient life, or studying if Mars was able to sustain life. But the InSight mission was a bit special, because the aim of this mission was not to understand if life was going on or life was possible on Mars at a given time, but it was dedicated to the understanding of the processes of planetary differentiation, how the planet form and how it differentiates. And so for that, InSight was dedicated to study the internal structure of Mars. And in particular, it was following the footsteps of terrestrial geophysics at the beginning of the 20th century and trying to understand what is the thickness of the crust, what is the structure and composition of the Martian mantle, what is the size and density of the core, the distribution of the seismicity and the heat flow of the planet. And regarding that aim, it followed the same questions that the Apollo mission tried to answer on the moon about 50 years ago. So the PI of this mission is Bruce Bannert from the JPL, from NASA. PI is the principal investigator. And so this mission had, in particular, three main instruments to study the internal structure of Mars. The seismometer, which was built in France by the IPGP and the CNES. The HP-cubed instrument, which was dedicated to the study of the heat flow. And this HP-cube instrument was built by the German, but unfortunately it didn't work. And the RISE instruments that was dedicated to the study of the rotation of Mars. So this is a picture of the InSight landers that landed on Mars with these two solar panels that allowed its InSight to process. So InSight followed the Viking mission. The Viking mission, Viking 1 and Viking 2 in 1976 also had a seismometer working, settled on the landers. However, during Viking 1, the seismometer was the only instrument that didn't work. And for Viking 2, the seismometer worked, but it was still on the deck of the instrument and was not settled on the ground, and it did not measure any, it did not recorded any signals. It only recorded noise and wind as it was shaked by the landers. So InSight was settled the first working seismometer at the surface of Mars. It was selected as part of the Discovery program in between with two other missions in 2010, and then it was selected as a winner mission in 2012 for launch in 2016. However, in 2016, there was a problem as the sphere that was supposed to contain the seismometer was leaking. It should have been under a vacuum. And so there was a 2 years delay, and in the end, InSight was launched in 2018, on May 5th, from the Vandenberg base in California. And it took 6 months, the travel to Mars took 6 months, and it finally landed on Mars on November 26th in Elysium Planitia. It was designed to work for 2 Earth years, but it was prolonged for 2 more years. So in the end, it worked for 4 years. So InSight landed close to the equator at 4.5 degrees north and 135 degrees east, close to the Elysium volcano here. So this is Olympus Mons, the highest volcano in the solar system. You probably heard of it. This is the Tharsis Mons and Valles Marineris, this big rift. InSight landed here in Elysium Planitia, close to the equator and close to what we call the dichotomy, which is the limit between the northern hemisphere and the southern hemisphere. You can see that this is the topography of the planet, and the southern hemisphere is much higher by several kilometers on average than the northern hemisphere. And this is InSight, the lander here, taken just after its landing. So InSight consists of 3 main instruments: this seismometer, the HP cube instrument, and these RISE antennas. And I'm mostly going to talk about the results of the SACE and RISE instruments. So these RISE instruments consist of 2 horn-shaped antennas and a transponder that allow the direct radio communication in between the Earth, the very large antennas of the Deep Space Network of NASA, and Mars. And in particular, it allows to measure the distance in between Mars and the Earth with a remarkable precision. So you may know that the distance between Mars and the Earth, when Mars is closest from the Earth, is on average about 79 millions of kilometers. And this radio connection allows to measure this distance with a precision of 10 centimeters. So very good precision. So the goal of this instrument is to reconstruct the rotation of Mars, and in particular the precession and the phenomenon of nutation. I will talk to you about that later. And because this rotation is very sensitive to the internal structure of Mars and to the size of its core in particular. So the measurements in between of the distance between the Earth and Mars were taken for an hour. So it consists of an hour-long measurements per week, which were reduced to 30 minutes during the extended mission. So during the last 2 years of the mission. So what is the principle of these measurements? So Mars is flattened. The polar radius of Mars is about 20 kilometers less than the equatorial radius of Mars. And because of this, and because Mars is tilted on the ecliptic plane, there is a torque wave from the Sun that excites the rotation of the axis of rotation of the planet. And this phenomenon is called precession. So Mars has a precession, and InSight and the RISE instrument allowed to measure the rate of precession of Mars. And this after several missions, in particular after Viking, which occurred in 1976, and after Mars Pathfinder as well, so over several decades. So this allowed to measure the rate of precession with more and more precision, given it lasted for several decades. So this precession depends on the distribution of mass inside the planet, and hence on the moment of inertia. So there is the moment of inertia the vertical moment of inertia relative to the axis of rotation, and the horizontal moment of inertia relative to the equatorial plane. This rate of precession, when we apply conservation of angular momentum of the planet, given the torque wave from the gravitational torque wave from the Sun, the rate of precession depends on these two moments of inertia, polar and equatorial, as well as on the distance from the Sun, or on the obliquity of the planet, on its eccentricity and rate of rotation. And so we can express this precession rate, and we have been able to measure this rate of precession with the InSight mission, and hence to precise the moment of inertia of Mars, which has constrained the internal structure of Mars. So you see that with the InSight mission, we have a better precision. So before the InSight mission, we had a moment of inertia of 0.3639, and after, we have a better precision and a moment of inertia of 0.364019. But I will tell you the consequence about the structure of Mars in a few minutes. So another phenomenon that affects the rotation of Mars is called the nutation. Because the torque wave from the Sun on Mars and from Phobos and Deimos is time dependent, this excites some oscillation in the phenomenon of precession that are here in red, and these oscillation in the precession are called nutation. And InSight has been able to detect the free core nutation, which is a specific oscillation caused by the differential rotation of the liquid core compared to the rigid solid mantle. And this has been able to constrain, to give strong constraints on the size of the core of Mars. So in particular, for the first time, we have measured the nutation frequency and the nutation amplitude, the free core nutation frequency and free core nutation amplitude. And both of these quantities are a function of the inertia, the moment of inertia of Mars, of the mantle, of its mantle and of its core. Same thing for the nutation amplitude. And this has given strong constraints on the core size. So in particular, the free core nutation amplitude depends on an amplification factor that strongly depends on the core moment of inertia and hence on its size. And InSight has shown that this factor is rather large, so it's consistent with a liquid core. So that the fact that this factor is quite large shows that the core is liquid, and its value shows that the core radius is between 1780 kilometers and 1885 kilometers. So it gives strong constraint on the core radius. Before InSight, estimates on the radius of the core of Mars has been given between 1700 and 1850 kilometers. So you can see that here with InSight, we show that the core tend to be larger than what we previously thought, given geochemical and geophysical data before the mission. So the fact that the core is rather large shows that this core, the core of Mars, should have a rather small density in order to be consistent with the inertia, the moment of inertia of Mars. So this points to a core density of about 6,000 kilograms per cube meter, and it signifies that the core should contain a rather large sulfur fraction in order to have a rather small density. So the core sulfur fraction is estimated to be between 8 and 20%, which is quite significant. for this core size and core density. So from the RISE instrument, we got some estimates on the core size, on its density, and with this, and from estimates of the thermal structure of Mars, we can say that the inner core is unlikely to be present because there is likely a large core sulfur fraction, and hence the core is close to eutectic, to the iron sulfur eutectic, and the temperature that we expect in the core of Mars is too large to allow for the presence of an inner core. Plus, we did not detect any free inner core nutation, but we don't detect it for the Earth as well. So an inner core is unlikely to be present on Mars today. So this is for the main results of the RISE instrument. Now I will talk more about the SICE instrument, which is this seismometer. So this seismometer was built at IPGP and CNES in France, in Paris, and the principal investigator of this instrument is Philippe Lognonnet. This instrument has necessitated 20 years of development. It consists of three pendulum, three very broadband seismometers that are highly sensitive. They are capable of detecting displacement of the size of a hydrogen atom. So it's a very highly sensitive instrument. It is sensitive to a frequency range of 10 to the minus 3 to 10 hertz. And so these are the three VBB, three very broadband seismometer. This seismometer, so a three-component seismometer, are placed in this sphere, which causes the mission to be delayed for 2 years, so under a vacuum, and this sphere is itself placed under a structure that isolates it from the atmosphere of Mars. So this is here it's the total structure. So there is 3 VBBs, but also 3 short period seismometers that are here. And this short period seismometer was built by the University College London. These short period seismometers are placed on the sides of this of the sphere. And the total instrument, you will see on a movie later, is placed below a thermal and wind shield that protect the seismometer from the atmosphere and the thermal variation at the surface of Mars. So this is again InSight with the seismometer when it landed at the surface of Mars. So the seismometer was initially on the deck, but it was placed on the ground with the arm, here, the electronic robotic arm. And this was very important because, as I told you during the Viking mission, the seismometer was placed on the deck of the lander, and it did not measure any seismic activity because it was too shaken by the wind. So here is when we landed, the first picture we have, and this is when we put the seismometer on the ground. Oops, sorry. When we put the seismometer on the ground. And this is the tether that allows electronic data to be transferred to the deck from the seismometer. So we had about a picture each day. And this is when we put the the thermal and wind shield on top of the seismometer to protect it from the wind and from thermal variation. Thermal variation at the surface of Mars are very large. They can be about 50 Kelvin per day. So one sol is one Mars day, and it's about the same as an Earth day. So this is after 70 days at the surface of Mars, and so the seismometer is protected against the wind. And it's only when the seismometer was protected by this wind shield that we have been able to detect seismic signal at the surface of Mars. Before that, it was too shaken and the signal was too noisy. So again, some movies, some picture that we took with the vast plains of Elysium that you can see, and the protection of the seismometer. So we have settled one seismometer at the surface of a planet, but the problem is now to understand the seismicity of a planet with only one seismometer, and in particular to locate Marsquake when we measure and when we record the Marsquake with only one seismometer. So at the beginning, before the mission, we thought that we would locate Marsquake using surface wave, as surface wave travel at the surface of Mars, and we know their path at the surface of the planet. So with a different arrival of a surface wave, so here for a Rayleigh wave, the first arrival, second arrival, third arrival, we would be able to reconstruct the path of the wave and in particular the distance, the epicentral distance from the quake to the station. However, we did not detect many surface waves, and it took a while to detect surface wave for a given Marsquake. So at first we only detected body wave, and so we had to use body wave and the arrival time of different seismic phases, such as P and S wave, or SS and PP wave, to understand the structure of Mars. So what we did is that we use a very large number of a priori seismic velocity model for the interior of Mars, and we inverted the structure of Mars given the arrival, the time of arrival of several seismic phases, such as P wave, PP, and S wave. And we refined this seismic model each time we had a new quake. So this is how we get for instance, the delay time in between the arrival of the S and P wave gives the epicentral distance of the quake from the station. And so this gives a great circle for the location of a quake. And then with the polarization of the P wave, the direction of motion of the P wave, we are able to constrain the azimuth of the quake and then to give a location for the quake. So these are the Marsquake we have been able to locate at the surface of Mars. And many of these quakes are located in what we call Cerberus Fossé here, which is a region of Mars that was previously, before the mission, it was pointed as a possible active, seismically active area on Mars. So here is Cerberus Fossé and InSight, and you can see that many of the quakes we detected and we have been able to locate are in this region. So again, Olympus Mons, the rift Valles Marineris, that is very well known. But in fact, we detected many quakes. We detected more than 1,300 events, more than 1,000 events. But not all of these events are teleseismic quakes. Many are only thermal cracking or signals that we don't really understand. Many are also due to meteorite impact at the surface of Mars. And many are also quake, as we have on Earth. So this is the soil. So after more than 1360 days at the surface of Mars, and the time of the day. And what you can see in color scale is the intensity of the signal, and in particular, when the color is yellow, it means that there is a lot of noise on the instruments. And this is because we are during the day. So this is the day. The Martian atmosphere is very active because it's being heated by the sun. And so you can see that the noise is too large for us to measure any seismic activity. Most of the signals, most of the seismic, most of the quake and the seismic signals have been measured during the night. So you can see here and here. And this period is a very active period. It's a period of dust on Mars. It's a period of the year of dust and storms, sorry. So again, the same period of storm. So we differentiate the signal by their frequency content, and in particular, if they have a high frequency content or low frequency content compared to the frequency of 1 Hertz. Low frequency signals, low frequency events are what we think are teleseismic quakes, similar to earthquakes. Those high frequency quakes, we also think that they are caused by Mars quakes, while the very high frequency quakes might be due to meteorites. So this is an example, the first rather large event that we detected on Sol 173. Its magnitude is estimated at 3.7, and it's a low frequency event. So you can see two arrivals, the P wave and the S wave, but also some signal that pollutes the seismic signal that is called a glitch, and that the team has to remove in order to treat properly the signal. And we don't really know what is the cause, the origin of this glitch, but that perturbs the seismic signal. So P and S wave, and the spectral content of this low frequency event, S0173, and of other low frequency event, so frequency. And you can see that the noise is in black, and you can see that these low frequency signals have a frequency signature higher than the noise for low frequency content below 1 Hertz. This is a high frequency event. So you can see, so this is 4 minutes, and sorry. Okay, so it's a high frequency content. Again, we can see two arrivals for this signal, and this is a spectral, the spectral signature of this high frequency event. And you can see that for this high frequency event, the spectral signature is higher than the noise, in black again, for a frequency higher than 1 Hertz. So we interpret these different events, low frequency and high frequency event, as Marsquake, teleseismic Marsquake that have different paths inside the planet. For the high frequency event, we still have two different, two different arrivals that we call P and S arrival, but we interpret this arrival as being, or these events and their path, the path wave, the wave path, as being confined to a crustal layer. While for the low frequency event, we think that the ray path has gone through the mantle of Mars. So this is the core, the mantle, and one crustal layer at the surface that is able to confine the ray path of the seismic waves. So this is the largest event we have detected at the surface of Mars, S1222A. So it occurred on Sol 1222. So after almost 4 years of mission, its magnitude is about 4.7, and it occurred on May 5th, 2022. This quake has been located in the plain of Elysium here, so close to Cerberus Fossé again. And you can see again the P and the S wave. So with all these signals, we have been able to constrain the size of the core again, but with a different technique than with RISE, and in particular by studying the SES, so the seismic phase, the S wave that is reflected at the surface of the liquid core. So this is after some treatment, some polarization filtering, the signal, the SCS arrival here for the event S0173. So one of the largest events we have detected at the surface of Mars, and so that has allowed the detection of this SCS. So the S wave reflected at the core mantle boundary. So using a priori model, the arrival of the SES and the time of arrival of the SES for different Marsquake has able to constrain the size of the core of Mars with seismology this time to 1790 kilometers and so between 1790 kilometers and 1870 kilometers. So you can see that the estimates for the size of the core from RISE is very close to that from SEIS, and those two are very independent. So the same size for the core, a large core size, again we see a large core using seismology, and hence probably a large sulfur content and a small density for this core. So larger than what we thought previously. So before, I remind you that we favored a smaller size core in between 1700 kilometers and 1800 kilometers. So a large core. However, so this is the consequence of this liquid core. So the core is liquid. So we know that thanks to the RISE instrument. And this is the shadow zone at the surface of Mars as seen from InSight. So this is a location of InSight, the surface of Mars, and all the faults at the surface of Mars, normal faults in red and contraction, reverse fault in blue. This is Olympus Mons, Tarsis, and here you can see the faults of Valles Marineris, the normal faults of Valles Marineris, the rift, and the shadow zone as seen from InSight. What you can see that the shadow zone covers most of the normal faults of Rise and Tarsis, unfortunately, which means that we won't really see many quakes from this region, given that they have to go through, the wave have to go through the liquid core. However, InSight detected the quake or the seismic signal caused by a meteorite that occurred in the shadow zone. So here, it occurred around here, close to the Tarsis Montes. And this event was called the Christmas event because it occurred on the Christmas day, on December 24th, 2021, the 1000th day of the mission. And we have imaged the crater with the HCRS camera at the surface of Mars. So we have the size of the crater. And one day before it occurred and one day after it occurred, and we recorded the seismic signal caused by this event. So for the story, we first recorded the seismic signal, which was then located using seismicity and the different arrival time of different seismic phases, located the signals with polarization, and then looked for image of a crater around this location and found it. So that was a great discovery. And so this meteorite happened in the shadow zone, which means that the P wave we see is not the direct P wave, but it's a P wave that is diffracted along the core mantle boundary. So it travels along the core boundary, the core mantle boundary. And it seems to, the arrival time of this P wave seems to be a little bit delayed compared to what we predict with a spherical model of the interior of Mars. So this suggests that there might be a layering at the surface of the core, and some authors from the mission suggested that the core mantle boundary has a very specific structure with a metallic core that is close to a radius of about 1,700 kilometers, topped by a silicate liquid. So this suggests the presence of a basal liquid layer at the base of the mantle, a basal magma ocean still present today at the core mantle boundary. But this is only with one event that we have this suggestion. Now with seismicity, we also learned about the crust, and this is what I will present you here. So we used the receiver function method to determine the structure of the crust below the station. So receiver function method allows to image interface depths where P and S waves are reflected and converted below the station. So these P wave arrival, converted and reflected, are detected in the coda following the arrival of the P wave. And with this receiver function method, we have been able to determine that the structure of the crust below the station is layered with 3 main layers and Moreau depths, so crust-mantle interface located in between 27 and 47 kilometers at depth. So the total crustal thickness below InSight is between 27 and 47 kilometers, and it is layered with a very low velocity layer at the top. So this is Vs, the velocity of the S wave, so you can see it's quite low at the top. So it suggests quite high porosity of this layer, and then two other layers. So with this anchor point below the station and using gravity and topography data, we are able to reconstruct crustal thickness maps. So gravity and topography gives crustal thickness or relative variation of the crustal thickness at the surface of the planet, and the determination of the depth of the MO at one point allows to ensure these crustal thickness maps. So here is a crustal thickness map for a given density of the crust of 2,900 kilogram per cube meter. So you can see a crustal thickness going from less than 10 kilometers to more than 120 kilometers thick below the Tarsis Mons. InSight is here, Elysium volcano here, Olympus Mons here, and Valles Marineris. So with this crustal thickness map, we have the bulk average crustal thickness on Mars, that is about 50 kilometers. And we are able also to have the average crustal thickness in the different geological provinces. And this graph presents the average crustal thickness map, the average crustal thickness at the surface of Mars as a function of the crustal density. So these maps are assuming a given crustal density. We also have regional constraints on the crust structure using different arrival times for seismic phases. And the arrival times regionally suggest that there exists a large a high velocity layer at the base of the crust regionally. So this is the mantle with velocity larger than 4 kilometers per second at a depth of about 50 kilometers here, and a large velocity layer at the base of the crust is probably regionally present. The origin of this layering might be caused by porosity, in particular in the first 10 kilometers. We have seen that below the station there is a very low velocity layer. But it could also be due to a difference in composition in between those three layers and a difference in crystallinity of these rocks. And we don't really know. There are several possibilities. So what we have shown is that given the crustal thickness map on Mars and given the abundance of heat-producing elements at the surface of Mars, we think that 50% of the radioactive heat-producing element, which consists in a heat source of Mars, are concentrated in the crust in order to avoid widespread melting in the mantle. So these are different geodynamical models showing melting in the mantle of Mars for different distribution of radioactive heat-producing elements in between the crust and mantle. And only when we put a lot of heat-producing elements in the crust, we have low partial melting in the mantle, and only melting below Tarsis at the present day. If there is too much heat-producing element in the mantle, we have partial melting everywhere, which is not possible since we only observe evidence of volcanism, recent volcanism on Olympus Mons and Elysium at the surface of Mars. So both geodynamic modeling and constraint on the crust thickness provide insight in the distribution of heat-producing elements within the planet. Now, what can we see in the mantle of Mars from seismology? So there is Mars is different from the Earth in terms of gravity. The gravity of Mars is lower than the Earth. It's about 3.7 meters per square second compared to about 10 on Earth. And so within the lithosphere, where the temperature increases a lot with depth, the effect of temperature might be dominant on S wave compared to pressure. So you probably know that S wave, in particular, the velocity of S wave are very sensitive to the temperature and to the pressure. S wave velocity tend to decrease with temperature and to increase with pressure. And given that in the lithosphere the temperature increases a lot with depth, the effect of temperature on S wave could be dominant on Mars. And this is what we investigated using arrival times and using the amplitude of the S wave. So these are different seismic signals, seismic signal for different quakes at different epicentral distance from the station. You can see that you detect the P wave here, but the amplitude of the S wave tend to be low at relatively large epicentral distance, and this might be due to the temperature increasing in the lithosphere of Mars. So with the amplitude of the S wave, we are able to say that the lithosphere of Mars is probably quite thick, about 400 to 600 kilometers, and the temperature gradient in the lithosphere is about 2 Kelvin 2022. After 2 years of extended mission, it was supposed to last only 2 years, but in the end it lasted 4 years. And it stopped because it was covered by sand, and so the solar panel were not able anymore to provide enough power for the seismometer to work. So this is a picture at the end of the mission and at the beginning of the mission. So with InSight, we have been able to constrain the size of the crust, the thickness of the crust, the thickness of the lithosphere on Mars, and the thickness of the radius of the core. We have shown that there is probably no inner core inside Mars. And so this has been able to also constrain the temperature structure inside the mantle and the composition of the mantle of Mars. And so we think that these data are still being understudied and will give even more information about the structure of Mars in the future. And I'm going to stop here. I thank you very much for your attention.
So thank you very much, Chloé. Any questions?
Do you have questions? Yeah.
Well, first of all, thanks a lot for this very informative talk. I have a question. So the evidence for a liquid core comes only from the nutation, or there are observables?
No, there are several things that tells us that the core is liquid. Before the mission, it was already suggested that it was liquid because of I don't know if you are familiar with the Love number, but the effect of the tide of Mars, so deform Mars and change the gravitational field of Mars, and by studying the change in the gravitational field of Mars as a function of time and as a function of tide, we are able to give constraint on the fact that the core is liquid or not, and the deformation is rather large, which suggests a liquid core. Already before the InSight mission, we had some evidence that the core was liquid. So there is the RISE mission and the amplification factor for the nutation that suggests that the core is liquid, and also the fact that we observe the SES and not really the PCP in terms of seismology. The SES, so S waves are not transmitted through the liquid, and they are reflected at the surface of the liquid, and we indeed see much more the SES in the seismic phase than the PCP, because the P wave are transmitted through the liquid core. So different evidence that the core is liquid.
And the core is in convection, so there is a magnetic field?
At the present day, there is no magnetic field on Mars, but there has been some magnetic field because there are remnant magnetization in the rocks at the surface of Mars. But at the present day, there is no magnetosphere.
So it's a liquid core, but it's not convecting? Or we don't know.
It's probably convecting, but not strong enough for a dynamo to occur at the present day. But in the past, around in between 4.5 to 3.8 gigayears ago, there has been a magnetic field.
Another question here.
Hi, thanks for the talk. Towards the end, you said actually the gravity we know is lower than Earth.
Sorry.
Gravity in Mars is lower than Earth. So I was wondering, what's the actual effect? You were saying that it's affecting temperature and pressure, right?
It affects the velocity of the effect. So seismic wave velocity are sensitive to pressure, and gravity affects pressure.
So my question was into that, like, how do you compare, or does gravity have an effect on the seismic signal that you're studying here in Mars, and can it be compared to the seismometer that we use in Earth, for example?
So technically the seismometer has to be
calibrated.
When we settled the seismometer, we had to adapt it to the gravity of Mars initially, but in terms of seismic signal, gravity affects pressure. So the range of pressure within Mars is much smaller than on Earth because the gravity is 3 times smaller, and also because the planet is smaller. The radius of Mars is 3,400 kilometers. And so the range of pressure is much lower, and so the travel time will be affected by that because the velocity will be lower as the velocity of the seismic wave tends to increase with pressure because the elastic constant are sensitive to pressure, and the density is sensitive to pressure. So the travel time of seismic waves are affected by pressure and hence by gravity.
Hello, thank you very much for your talk. I'm not a seismologist, but I'm very impressed of the amount of data that you gather from just one seismometer.
Yeah.
So my first question is, why just one? I guess it's a technical problem to...
So initially, like 20 years ago, the plan was to set on different seismometers, but of course the cost is too big, and so only one seismometer was settled because the people that built this mission, Philippe Lognonnet in particular, Bruce Bannert, show that with only one seismometer we could already do some seismology because this is a highly sensitive instrument.
Okay, so my second question is, have you tried, for example, to display one seismometer with similar technology in Earth and compare the results that you would obtain comparing to the results with all the network of seismometers, but just comparing to just with one?
Yeah, of course. There have been a lot of tests done on the Earth with only one seismometer to test this idea. So before the launch of the mission, and of course even for the design of the mission, this was done. But of course, so I'm not a seismologist myself. I'm a geodynamicist. But of course, the seismic signals that we have on Mars and the information are much less constrained than what we have on Earth, of course.
And can you give, I don't know, like, I know it's impossible to extrapolate results as if you have more than one seismometer, but how close you are or far from data with less error as if you have more than one? I don't know if I explain myself. Like, if all these studies have been made in Earth with just one seismometer comparing to results with load of seismometers, how far are these numbers in Earth? And if this could be extrapolated in Mars? I don't know.
Yeah, I can't really say. Since I didn't do the study, I can't really say, I'm sorry.
Okay, thank you.
Another question, I'm coming.
Thanks. A couple of questions. One is on the geodesy side of the talk. The first part, you're looking at precession and nutation.
Yeah.
But you've got a fluid core.
Yeah.
And I can imagine that the angular momentum of the fluid core and the axis of rotation is different between the core and the crust, or the crust and the mantle. Wouldn't you expect to have wobble as well, like you've got on Earth?
Yeah.
Have you looked into that and have you seen anything?
Yeah, there is a Chandler wobble, and this has been studied before InSight, the Chandler wobble, which also caused some nutation, and it has constrained the moment of inertia of the mantle, I think. Yeah, but it exists. I don't remember the frequency or the periodicity, but this has been studied before InSight.
And the second on the seismic part, which is a bit on the technology, do you happen to know what's the shock rating of both the broadband and the SP?
The what?
The shock rating. So from how far you pretty much land in there. Imagine that you take the seismometer and you drop. Yeah. How many Gs would the seismometer stand?
I don't know. Yeah, I don't know. But I know it has been submitted to a lot of tests regarding acceleration, etc. before the launch. But I don't know exactly how many shock it can.
Yeah. And these both sensors, the SP, I guess that's ICL, right? Tom Pike.
Yeah, it's okay. Tom Pike. Yeah.
So the SP and the broadband, are those still lab units, or I know that units that come from a research endeavor, or I know that Tom was working with kinemetrics. Is the commercialization of those units being looked into and made available, or are they staying in the labs?
I don't know. I can't answer your question. I'm sorry.
Okay, no, that's fine. That's fine.
But there are some spare instruments for the VBB in particular that will be launched soon for the moon. Normally it should have been this year, but it's probably going to happen next year. in 2026 to study Moon with one station again, similarly to InSight. So it's going to land in the south pole of the Moon. It's in the frame of the Artemis mission, the NASA mission again.
And maybe coupled to the question that it was asked before, what kind of mission would you, looking into the future, you envision for ruling out, the presence of a solid core?
For ruling out the presence of a solid core, well, I guess we need more precision on the thermal structure and thermal evolution of the planet. Of course, seismology would help, but also constraint on the thermal structure and evolution would help. And in fact, this mission was supposed to measure the heat flow at the surface of Mars today, and the instrument didn't work, or I mean the measurements didn't happen. The instrument worked, but it did not penetrate deep enough into the ground of Mars to be able to measure the heat flow. So this would have given a lot of constraints, more constraint on the present-day thermal structure of Mars, and this would help for sure.
Thanks.
And we have a last two other questions.
Hi. A few disjoint questions as well. One is, so the sensitivity of the seismometer was from 0.001 hertz to 10 hertz, something like that?
Yeah.
What was the distribution of the earthquakes that you found over that period? And why was it cut off at 10 hertz?
So the short period seismometer, the sensitivity of the short period was up to 40 hertz.
Oh,
so
okay.
They both cover a different range, but you can see the frequency range of the quake. So this is for the high frequency, so up to 10 hertz. And for the low frequency, you can see down to 0.1 hertz, 10 to the minus 1. And the noise in black.
But these are for individual events, right?
Yes.
So, I guess, do you have an idea of the distribution over? Well, I see what you mean. You're saying that it just covers the whole
in
range.
black, it's the noise. So you can see that a little bit below 10 to the minus 1 hertz, you can have some signal, but those are the largest events.
Okay. And then another thing is, towards the beginning, you showed a general geography of Mars.
Yes.
Which I'd actually never seen before.
Oh, I should have put more then.
Is there some so I was very struck by the giant basin on the bottom.
Yeah, Hélas and
Hemisphere?
Argyre. Yeah.
What's it called?
Hélas and Argyre basin.
Oh. Do we have some explanation for the evolution of the geography? Like, why is it so deep there? Why is it so deep in the northern hemisphere? And
So actually, this difference in topography in between the northern and southern part of Mars is not understood yet. It's not understood yet. When we look at this, at the surface of Mars, so what we can see first is this very large Tarsis dome, and so this is caused by volcanism. And it's so large because there is no plate tectonics on Mars. So as there is no plate tectonics, volcanism caused by a plume is very important and causes the crust to thicken a lot with time as the plume doesn't move relative to the position at the surface. So it's still ongoing at the present day here. And so this is a striking feature. And then there is this dichotomy in between the north and south, which is not yet very well understood. And when scientists first saw that, they thought that Mars has undergone plate tectonics at some point. But in fact, there is no alignment of volcanoes. Gravity is not suggesting any subduction there. And there is no evidence at all of ancient past plate tectonics on Mars. So plate tectonics probably did not occur at all. And this is caused by another process.
And the basin also on the southern hemisphere, is that maybe do we have any explanation for what that could be?
So these are caused by meteorite impact.
Okay.
And actually the presence of this low northern hemisphere, it has been proposed to be due to large impacts. It has been proposed to be due to internal activity, convection with only one cell, or other processes. So it could be external or internal. And these large basins are caused by rather large meteorite impacts.
And
Early on, probably around 4 gigayears ago, 3.5 gigayears ago.
And finally, what was the motivation for the landing site of InSight and for the position of the seismometer?
Yeah, that's a good question. In fact, as you saw, we are far from one active place, Valles Marineris, and all the faults caused by Olympus Mons. So the motivation was technical first, because you want to have a very flat surface to be able to land without danger. And also one of the motivation was to land in a place where the regolith, the ground, is quite deep for the instrument that was supposed to measure the heat flow to penetrate deep enough. So this instrument, HP cube, require. Let me show you here. So HP cube, it's a mole that was supposed to penetrate 3 to 5 meters deep in the ground of Mars. So the ground of Mars is probably very porous because it has been fractured and affected by meteorite impact. It's a very old surface. And as on the moon, it has been subjected to a lot of meteorite impact, so it's very much porous, and we call it a regolith. And so we wanted a very thick regolith. And so we landed there because you can see the ground seems quite porous, and this mole could penetrate normally deep enough. But in fact, it probably encountered a big rock and got stuck very, very close to the surface.
Okay, thank you. So thank you all for your questions, and let's
Thank
thank
you very
Chloé
much.
again.